Good evening, everyone. Can you hear me?
Yes, sir.
Okay, great. All right. So today is week two's Solve with Instructor session. So before we begin, do you have any questions that you would like to ask? All right. So let's begin. So in this week, the topic of linear regression was formally introduced, and all the components of that machine learning technique have also been covered. So focus of this week's content is that you know what is linear regression, what kind of data it accepts and it works with. Um, you know what a model is. You also know how to optimize it and how to get to the right solution. When I say right, I mean ultimate solution. And you also know what a model looks like. How would you gauge which model is better than the other? And at the end, once you have some candidate models, how do you measure which is the best one?
Hi, Swarnim.
Hi, good evening, sir. So glad to have you, sir.
No problem. Yeah. How are you doing?
I'm doing good, sir.
So if you have already started, you can continue. No problem.
Sir, I was just taking some introductory points about this week. So please go ahead, sir. Yes.
No, go ahead. You finish it off and then I can take on.
Yes, sir, I'm finished.
Okay. So are there any questions from the participants? Otherwise,
Sir, this is Srinivasan here. Can I ask a question?
yeah, sure. Please go ahead.
So it is actually a bit of a larger this thing. So I had thought that MLT and MLP will kind of go together. And I'm very clear that MLT, we are looking at basic theory, and then that way we do things from the beginning, right? And MLP is more of actual what we will do as a practitioner.
Correct.
Right? But is it something that will the week contents don't seem to be together, so they seem to be slightly off? Is that what is expected, or will the weeks also be kind of in lockstep between these two?
So we have tried to align these courses. Maybe there is a delay of a week. So what you learn in theory, we give probably a week to for you to catch up, and then we take practice session. So that is one format. But mostly they are coming in the same week, except for maybe a couple of weeks. Yeah.
Okay, sir. And then I think I did have a question about the mathematical foundations required. I think we had discussed it in the morning also.
Yeah. Sure. No problem.
And then there's one comment I couldn't add at that time, is that statistics, we had actually done a very good job. And a lot of us, if you ask the statistics students, statistics 2 particularly, a lot of the students love, I should say love the way Professor Andrew presents it.
Okay.
In the last 3-4 weeks, he has covered pretty much all the important distributions required and all that stuff.
Okay.
So that way, when somebody asks a question, I was about to tell Shreya, that person who asked the question, that we just refer to that week, you will get those fundas cleared. So you were not sure whether how much was it covered, but I thought I'll just share that comment.
No, thanks for doing that, because so most of the things what I'm doing is I'm actually assuming that because people have done and students have done some previous courses, things would have been covered in those courses. And certain things, I'm not getting into too much details of it actually. Yeah, thanks for sharing.
And thank you, sir. And definitely like the way you have taken this so far. Like the first 2 weeks have been amazing. I didn't expect this much of coverage and this much of depth actually. So hopefully we'll be able to catch up. Thank you, sir.
Sure, no problem. And yeah, thank you for your kind words. Yeah. Someone else also was trying to speak.
So
Yeah.
this is Shreya. I'm sorry. I just want to add a quick thing. Like I just heard what Srinivasan sir said.
Sure.
While we've learned all these concepts, I think I'll just reframe my question. I mean, my request to say that it would be better to understand how the code is implementing these things. Like not the mathematical explanation, but what is the code doing while implementing these things? Probably that's what I want.
I see. I see. Okay. Okay. So from practice perspective, we are not getting into the coding details of it because goal in practice course is to make you familiarize with the tools that are available in scikit-learn. But I can definitely point you to the code because scikit-learn is also open source, and we can figure out how that is done. So there will be some glimpse of that when we train naive-based classifier, right? When we learn naive-based classifier in MLT, we will be implementing some of these things, how to do estimations, how do you estimate parameters of statistical distributions or probability distributions. So we'll be covering some of those aspects actually in naive-based classifier.
Sure, sir.
Yeah.
Thanks.
So, but in the techniques course, it's I would have assumed that it's essentially the same thing, right? Because what we are doing in NumPy is what essentially gets packaged as scikit-learn and gets used in the theory course. There may be a bunch of other heuristics that people use because it's a fairly large library and so on. But essentially, it's the same thing. What we do in NumPy here is what is scikit-learn there.
Exactly.
How correct is that?
That is almost correct. Only thing is that because there are certain corner cases. So when we write the code in NumPy, right, or even whatever code that we are implementing in NumPy, we sometimes we couldn't take care of certain corner cases, like if you're taking log of 0 or some such kind of cases. So this sklearn library takes care of a lot of these kind of things, and their library is a bit more robust. And it also has implemented some of the well-known algorithms in the field, which are researched and presented in top conferences. So those algorithms are also implemented. And plus there is something called as practitioners approach, right, where there are a lot of heuristics that are well known in the community. So those are also included in sklearn library, which are often not possible for us to implement from scratch. Yeah.
It could be something as small as always normalize data before doing something that it'll automatically instead. Here we'll have to do everything.
Yeah. But a good thing about sklearn is that it also gives you control over it. For example, normalization, it might be provided as a parameter, or you might have to do it explicitly, something like that. So sklearn implements it as well as it also gives you control to pick and choose what you want. So that's why
disable it also.
Yeah. So that's why a bit of understanding is required. But good thing about scikit-learn, right, as I said in the week one, right, it uses sensible default values for most of the things. So even if you do not do anything, if you get a data set, you can actually use scikit-learn estimator to train the base model pretty quickly. You don't have to set parameters. You don't have to worry about setting parameters, right, and other things. Most of the time it uses sensible default values. And that's where this experience or well-known hacks in the community, right, which are included in the library. Yeah.
Thank you.
No problem.
Sir, in one of the when you use the normal equation, right?
Mm-hmm.
There you use that pseudo inverse of x multiplied by y, right?
Yeah, that's correct.
Yeah. So, what is that pseudo inverse? Like, is it different from what is inverse, or?
Yeah. So what happens is that sometimes matrix is not invertible if there are, let's say, dependent variables. That time we need to go for pseudo inverse actually. So pseudo inverse is more, I would say, it is more robust. So even if there are some issues in the input matrix, like linear dependencies or something like that, PseudoInverse takes care of that.
Okay, so the original equation like x transpose inverse, then x transpose y, that is equivalent to like taking the pseudo inverse.
Correct.
Okay.
That's right. That's right.
Okay, sir.
So, if I'm not wrong, when we talk about pseudo inverses, we are generally talking about the SVDs, right? In the sense. So, okay, later to that question. I just wanted to ask, we had used for learning rates, we had used a lot of trial and error method. Is there any robust way of finding it, or we have to just do it by ourselves?
Great question, actually. Yeah, learning rate is something which is, I mean, we call these parameters as hyperparameters. So learning rate is one of the hyperparameters. We do not train these parameters as part of our objective function. So you can think of hyperparameters as some kind of learning setup, some kind of setup, right? And these parameters are provided by the designer of the algorithm. So learning rate is one of that parameter, and we'll have to actually use this kind of trial and error method to select the right learning rate.
Actually, sir, I belong to a robust statistic background. Okay, so I found learning rates to be generators. Basically, it could be generated with the help of probability generating functions. So, is there anything like that which I think it won't be covered in the course? I'm sure about that, but
yeah, and it is not actually followed in the community. So the general practice in community is to fix learning rate in a trial and error method. And generally there are, so only way to check what is going on is by looking at the learning curves, right, that we have talked about, and figure out if your algorithm is learning with that learning rate or it is not learning, meaning it is overshooting the global minima, right? Then the learning rate is too high, or if your algorithm, the loss is going down too slowly, then learning rate is so small, then you basically increase the learning rate. So what people do is, generally people try, so generally the way I do it is I start with, let's say, 0.01 as a learning rate. And if it is too small, then I'll change it by, I'll multiply it by 10 times. And so I generally have 10 raised to minus 4, 10 raised to minus 3, 10 raised to minus 2, 10 raised to minus 1, and 1 as learning rates. And then, you can figure out which two learning rates. So this is how you can figure out the learning rate. You don't have to try too many learning rates like this.
So this is grid search.
It's a grid search, exactly. It's a grid search, yes.
Okay. So there is no distribution which we can actually.
No, actually, yeah, people are not doing it that way. Even in practice, people are not doing it that way. People rely on, this is how, there is a general there is a grid search that is performed for learning rate.
Okay, thank you so much.
No problem. And learning rate setting is quite critical for success of certain algorithms. And it will become a big problem when you go to deep learning, where we have to set learning rates properly. So you will soon learn HGD in sklearn, and you will see learning rate is not always constant. Sometimes you also have dynamically changing learning rate, and there are schemes for that in stochastic gradient descent. Yeah.
So when we go for a stochastic gradient descent, so we are seeing the prior one, right? Or no, the future one when we are doing it the stochastic.
No, so HGD, right? HGD is like, HGD is also it's a gradient descent with one sample at a time. I think it is not yet covered, no? Or is it?
No, it has been discussed about HGD.
Yeah.
But I am saying when we talk about when we go for such such implementations. So even for example, when we go for stochastic implementation, we are generally talking about the future by taking one sample at a time, right? So we are predicting the learning. So is there anything where we can predict the learning rate with the sample itself?
No, you can set up such kind of learning. You can set up such kind of machine learning problem, but it is not done that way. Actually. So learning rate is something which is specified, and it is hyperparameter, and it is specified by the designer. And you can at best do some kind of hyperparameter optimization using grid search or some such kind of thing. So think of learning rate as an outer loop for the training, right? So your training is learning and you're setting different learning rate to figure out which one works best. Right?
Okay, sir. Thank you, sir.
Okay. Thanks.
Sir, is there any like other than convexity, is there any other like characteristics that a loss function should have?
No. So
only like any
differentiability.
Differentiability, yes.
Yes,
Loss
yes.
function should be differentiable, yes. That is another thing. Correct.
Sir, one more thing. If we have
Sure.
a convex, but we can optimize non-convex functions too. So why just convexity?
So you can have non-convex functions. The only problem with non-convex function is that you are not guaranteed to reach the global
optimum. Yeah.
That's the only problem.
Because there are many global optimums.
In fact, when you learn neural networks or deep learning methods, their objective functions or loss functions are often non-convex.
Okay.
Yeah. So non-convex functions are not as such problem, but we will be able to reach some minima, but that may not be global minima. That's the only problem. But differentiability is important because the function should be differentiable for sure.
So whatever function is not differentiable, do we have some way?
People try to come up with approximation to that non-differentiable function. So original loss function is 0-1 loss function, right? I mean, let's say if you're doing a classification, if you're solving a classification problem, you have 0-1 loss, right? I mean, if you classify correctly, you get reward of 1. Otherwise, you get loss of 0. You get penalty. You get penalty of 1. And if you solve it correctly, you don't get any penalty. So that's the original loss function, which is non-convex. So then we have a lot of approximations to that. Sorry, non-differentiable, not differentiable. So whenever we have non-differentiable functions, we generally work with approximations to those non-differentiable functions. So we come up with differential approximations to those functions, and those functions become our loss functions. Does it make sense?
For example, if our data set is, if our random variables are following mod, okay, the data set is positive, like mod x function follow correct. So it won't be differentiable, but we have a minima in it. So what to do then?
If it is not differentiable, then we cannot actually use it, right? So there are a couple of ways, right? I mean, there are certain functions which are non-differentiable. So you can then follow some engineering approaches. Wherever it is non-differentiable, take either right or left derivative. So you will have to do some engineering tricks. But if you want to solve it in a mathematically sound manner, then you'll have to take an approximation. You will have to take a function which approximates your mod function and which is still differentiable.
Okay.
So sir, like say for example, like you have two loss function now. How to say like which loss function will be good? Like is there like other than like really going through that training and see the learning curve?
So generally there are a specific loss function that is used for solving a specific problem. So see, I mean, what is happening in loss function? In loss function, we are basically talking about how do you want to penalize, some kind of incorrect prediction by the model, right? So if you have multiple loss functions, I mean, there is no harm. You can basically try training with multiple loss functions and see which one works best for your problem. Ideally speaking, the loss function should come from the designer of the model, and loss function comes from the insights into the domain of the problem, right? So if you're solving some problem in some domain, you can come up with loss function which is suitable for that domain rather than using generic loss functions. So loss function is, again, I would call it as a hyperparameter, and you can choose one which works best for you. But I mean, this is really advanced machine learning, which we are talking in the second week itself. But right now, for this course, right, you can imagine that there are certain loss functions that are tied to certain kind of problems, and people are using those loss functions like that. So, for example, if you are solving the regression problem, you cannot use classification loss function. You will have to use regression loss function. Does that make sense, Rajiv?
Yeah. I mean,
yeah, actually says say for example, even in case of a regression problem, right? Like we are taking say for example squared error loss. Okay. Now for a two-dimensional case, like it is okay, like we can visualize. But say for example, if I take to the power 4, right? So that will again it is convex and your differentiable, right?
Yes. Yes.
And so like which one will be better? Like how I can like do a comparison actually?
So what is the comparison?
Actually, Rajiv, I think you had asked something about volatility in time series, right? Was it Rajiv or somebody else? I don't remember. But recently we had this discussion about in regression, what is volatility, especially if you think of time series.
Yes. I asked that question.
Now,
yeah.
so let me try and take an example. Now, I don't know what volatility is in stock markets, right? Now, I could use the standard mean squared error loss, or I could come up with a loss function which penalizes volatility.
Correct.
So that in that case would become a better loss function for me than sum of squared errors, or in the least square sense.
Totally makes sense. Yes, that's correct. But see, what you're basically doing is that you are trying to constrain the loss function, which is least square loss function, by adding some constraints that make sense for that domain, right? So that is perfectly fine, and you have to basically make these loss functions better and make it more meaningful for the domain. Yeah.
Okay, so sir, like just a thought, maybe like not good idea. Say for example, if it is a two-dimensional, okay, like where I can plot, okay, a paraboloid which has a like which is steeper, probably that will be a better loss function because the gradient will be more. Like you will be reducing the loss more. Like is there something that sort of intuition or nothing like that?
It is not like that. It is all about how you want to penalize a wrong prediction by the model. So loss function comes from how much penalty you want to apply whenever there is a incorrect prediction from the model. And depending on the situation, right, depending on the domain, maybe you want to have a very steep penalty if the prediction is off by a very small margin. Even that is acceptable if that's what domain demands. But again, I don't want to get into this discussion right now because it might end up confusing a lot of people. So right now, just think about it as loss function that makes sense for the problem that you're solving is a good loss function. And to your question, right, I mean, it doesn't matter, right? I mean, we have demonstrated things in 2D because that's easier to see, right, and experience, right? But these things generalize in the same way for large number of features, right? If you have large number of features, let's say thousands of features, and if you use squared error, still the function will be differentiable. It's just that you won't be able to visualize that function, right? But things will work exactly like how it works in two-dimensional case. So that is one important point that I want to drive home, because don't think about, just a minute. Don't think about using simpler thing because it is easy to visualize. You may not be able to generalize the model with small number of features. So that's why don't hesitate. I mean, it's okay to actually use large number of features, and things will generalize exactly like how it works in two-dimensional case. Okay.
Okay, sir.
Yeah, but thanks for a lot of interesting questions. I'm happy that you're thinking on these lines. These are interesting directions. Are there any other questions? So maybe you can pose these questions in the group and we can answer them in offline. Yeah, Tanvir, go ahead.
I'm just when we find the error, or basically the residual of the regression, we have to minimize the error also, right?
Yeah.
But
so
yet we have.
Yeah, go ahead.
So, and that is why we find the optimal weights or the optimal parameters, right? So, sir, but is there any way like when theoretically when I solve by hand, I see that there are methods where we can find the optimum error, and with the help of that error, we can find the optimum parameters. So, is there anything like in machine learning too where we can do? Because I'm very pretty much new to the subject.
So what we are doing right now, right? I mean, using gradient descent, we are doing exactly like that. We are actually defining the error function. And if you remember those plots, we had actually visualized how the error looks like. And when we are taking a step in gradient descent, basically we are coming up with parameters that minimize the error. And as we reach to the lowest error, the parameters corresponding to that lowest error are the one that are likely to give you the best performance. At least those are giving you best performance in the training set. And because training and test set are IID, they are coming from the same distribution, by that we believe that since it worked well on the training set, and we also check whether it works well on the test set, and if it works well on the test set, we believe that it will generalize well. It will produce similar quality of results in the unseen data. So we are doing exactly like that what you are describing, but we are doing this analytically and through the gradient descent precision.
Okay.
So there are two ways. One is gradient descent and second is normal equation. Normal equation is analytical and gradient descent is more like an iterative optimization procedure where we are doing it one step at a time. Okay.
Okay.
Are there any other questions or should I give it back to Swarnim? Okay. Swarnim, over to you.
Thank you, sir. Thank you for being present and answering the questions.
Sure, no problem. Thank you. Yeah.
Thank you, sir.
Thank you.
Okay. So I'm going to start with linear regression. Of course, this is the this week 2 introduces linear regression from scratch. So let's start by some of the fundamental questions that we deal with when we talk about linear regression. So before we do that, so let's talk about this question: what is supervised learning? So what happens in supervised learning? Are the labels available or they are absent?
Available.
They're available, right? That's the one. So supervised means you have some supervision by so supervised means the input and output pairs are available, and that's why we call the learning problem of such kind supervised. Next one is what is regression?
The first one.
Real number.
Right. So supervised learning problems are classified into two types. One is regression, the other one is classification. So first one, if the number, the output or label that you want to predict is a real number, then it is a regression problem. Otherwise, it's a classification problem. Okay. So now, before we start looking at what regression is, so first thing that we need is the data. Okay, so let's generate a data with these parameters. So the data will be generated with this formula. We have only one feature, which is X. We have Y, which is label, and M and C are the two parameters. So, since we will be generating the data, take M is equal to 3 and C equal to 4, and then add some noise to it. Okay. So, real world data, it is noisy because it could be because of many reasons. So first, it could be due to recording the data or the statistics that we captured because of that. And second thing is the process which is generating the data, there might be some randomness involved, and therefore we take this error or some noise into account. So your first task is to generate 100 numbers between 10 to 60, and the equation of those numbers should be y is equal to mx plus c, where m is 3 and c is 4 and add some Gaussian noise to it. Okay, take 2 minutes. You are supposed to use NumPy as as you like. It's something that we will be using quite often.
How many numbers between 10 and 60? 100.
100 numbers.
Thank you.
And as soon as you are done, you can paste your code inside the chat box, so I can see, and we can. I can copy and see how it works. Okay, I am already seeing answer from Jaydev. And just let's wait for 1 more minute, 1 or 2 more minutes, and let everybody follow up. Okay, I hope okay, input number is NumPy. There is one more solution from Sumit Kumar. 60 is equal. Okay. Send syntax. Okay. Okay, Sumit, your answer is also very valid. We'll talk about it in a minute. All right, so let me copy Sumit's answer and oops. So I want to add a code block, but want to hide this solution for now, just for a minute. Okay, so this is a solution I received from Sumit. Of course, he has taken NumPy and he has used random class, and inside that there is random int. So what we are saying is generate 100 numbers. The lowest number is 10, the highest number is 60, and just print that. Okay, that looks possible. Okay, so this is okay. So you have generated x. What about y, Sumit? We have to generate y also, right? Y is equal to mx plus c. All right, I have one more solution from Rajiv. Okay, Sumit. Okay, so okay, so this solution that I received from Rajiv, let me print that and execute this one. Okay, let's print. Okay, so we have these numbers. All right. So first thing that Rajiv did is he created. So Rajiv, where are the x points? So I assume this is x, right? This is how
Yes,
you are
actually
creating
that is
x.
X, and I also miss that range actually.
So it was numpy dot
Random dot.
Okay. this was it. Okay. All right. So we have quite different types of answers, So first one, I'm going to write the other solution that I received for the first time, which was from Jaidev. Okay. I execute this one. Okay, let me execute it and then print, let's say, just first 5 items. Okay, this is how it is coming. And so Jaidev has used a function called linspace. Nice. So anybody would like to tell me what this?
That is wrong, sir. You never said that the points have to be equally spaced. They just have to be some points between 10 and 60.
Yes, of course. So I didn't say which one is right so far, have I?
No, but it's the probability that you'll find 100 equally spaced points in any problem is very unlikely. So I think Sumit's answer is more correct.
Okay. Yeah, sure. So, we can work with all 3 types of generating methods. However, so, we can, so Sumit's answer assumes that, the points are absolutely random. That is fine, completely fine. I'm happy with it. That's not an issue. And we've multiplied by mx plus c. Yeah, that is fine. No problem. It is just that for conducting our experiments with linear regression techniques and different components of it, equally spaced numbers might be a little bit easier to handle. That's it. We can visualize things also easier. Otherwise, yeah, of course, your point is right. The real world data doesn't have to be uniform at all. And of course, we can work with this data also. It is just that we'll have to put in extra bit of effort to understand what's going on. So for this exercise, this session, and for the next task which will be coming up, we'll be using this code. Okay. So before we proceed, can anybody tell me what this linspace function do?
Yeah, it will generate 100 numbers between 10 and 60.
Right. Both inclusive, right?
Both inclusive, yeah.
Right. So it generates 100 uniformly distributed numbers starting from 10, and the last number will be 60. Okay. And what we did is, so this becomes our x data points or feature value. And then what we do is we multiply it with the slope, which is 3, and we add it with 4, which is the bias run or y-intercept, and we add some noise to it, some normal noise. So by adding this normal noise, we are sure that the noise which is being added lies between 0 to 1 for every point. All right. So this is the beauty of NumPy. So many things are happening quickly. If we had to produce the same effect without using NumPy or by for loops, this would have taken a many number of lines of code as compared to this what we are seeing.
Sir, I have a question.
Sure, please.
Sir, why the comma after 100?
It's unnecessary. Absolutely unnecessary.
Thank you.
Okay.
So does this make use of seed? This
Of
is not
course. So
okay.
See, of course, sure. So let me explain that point also. So right now, please notice that the first value is 31.81 something. I'm going to copy this one, okay, and I'm going to keep a record of it. I want to explain what the seed value does. So what we are doing is we are taking this thing. This is the only thing which has some randomization inside it. So this function randomly generates 100 points from normal distribution, but it generates that absolutely randomly. So every time we call it, it is going to give us different results. So let me call it one more time, and let's observe the first y value. Okay, we have recorded in this iteration. Let's execute it, and now you are going to see that the first value is something else altogether. Yes, the reason is because of this. So this is the random factor of our equation, and because of that, we are going to get different answers every time we are going to execute it. And this is okay, and many times very, very useful when we are dealing with real world data. But for now, when we want our results to be reproducible, I mean, let's say you share this, you create this entire collab, and whatever the data was produced and the results that you created, you want to share it with your friends, showcase them, or maybe they want to learn it. You want to make sure that whatever results or conclusions that you've drawn are valid, even if she runs your code. So for that, what we want to make sure is, we want to make sure that the data which is being generated, it is generated same all the time. Okay, for every time we do this experiment. So for this, what we do is, there is a method called seed, in which we provide a number, which is a seed number basically. Internally what it does is, even though we think that random numbers are generated without any input, but that is not true. Typically, either it takes the timestamp of the machine on which this function is being run, that as an input, and then does some function, executes some function on it, and creates a random number. But if every time we give that function exactly same number to start with, that is called a seed, then whatever function it applies to get the random number from the seed, it is going to be same. So now let's execute it. I've set it 0. Now there's 35.76. All right. Now let me execute it again, or I can copy this one. Okay. Now, if I execute it again, I'm still going to get the same number. You can notice this, 35.76. No matter how many times I run it this time, this piece of code, I'm going to always get the same output. Okay?
Yes, sir, got it.
All right.
I have one query. I mean, this seed we have basically linked with random. What about this linear space? Because that itself can generate all those different numbers in different execution, right?
Lin space is not a randomized.
Is not random.
Yes. It is basically saying that between 10 to 60, give me
just
equally
doing the equal
distributed
divisions.
Yes, exactly.
Okay, fine, cool.
Okay. Any questions so far?
So, but does seed really matter here? Because ultimately our task is to produce slope and intercept. And as long as we keep the noise small enough, most models should converge to that, right? Of course, if we did to the epsilon term, if we did a multiply by 20 or 30, that may cause a problem, right? But since the noise is very small, even if all of us had a different noise vector, and as long as the gradient descent is fine, we'll still be able to find the correct MNC. So do we really need seed here?
Yes, for only for one thing, for yourself. Let's say you do this experiment, you introduce some random process like this into your experiment, and you got some conclusions and produce some results. After 5 or 6 days, you come up and try to regenerate all those results. It would be good if you you have this concretized this random process, so that this is just for reproducibility and making sure that you run the experiments, you can share those with others, and they can also reproduce your results. So of course, if I remove this line, we will still be able to train the model. It is just that the weight vectors will be different for all of us, right? So for now,
initial weight vectors only.
No, not the initial weight vectors, the final optimized weight vectors.
Shouldn't they be near 3 and 4?
They should be, of course.
Okay. But I mean, I get your point. It's good bookkeeping habit, I guess.
Yes.
Sir, if you can please just run the value of x.
Run the value of x? You want to see values of x?
Yeah, I don't understand them.
Okay, so let me print its shape. Maybe that would make things interesting. So see, it's an numpy array with shape 100. It has only one dimension. And I can also print its first 5 values. Oh, I made a mistake. It should be
small x.
It is small x, right? Yeah, there it is. So first value is 10, and we increment by since all the data points are equally distributed. If you took any 2 consecutive data points and subtract them, you're going to get the same number.
Okay, sir. Okay. Thank you.
Okay. So is your question answered?
Yeah.
All right. Okay. And one more quick thing. Let's say if I want to figure out what does this function do? Are there any other parameters? How would I do it? Can somebody tell me?
Just put a question mark next to it and hit enter. That will show
Exactly.
up the doc string.
Exactly. Thank you. So for any method, if you want to take, you want to see the help of it, you can just type question mark, and type the method with which you want some help with. Random.random. As soon as I execute it, it gives me its documentation, and in which you can see all the other parameters also that you can set and use. Okay. All right, let's proceed. Now that we have generated data points, which are located, situated in variables x and y. Next thing is to visualize. Now take 2 minutes and write code to visualize x and y. Okay, I'm getting very quick answers. Tanveer, Jaydev, Deval, right? Okay, I think I've seen a good number of answers. So let's start with. Almost all of you have got. Right. There's one thing. Rishabh, I assume that your z is the x variable. Okay, so I'm going to just copy one of the answers. Let's take Deval's answer this time. Okay. So first thing that we have to do is, of course, we have to import this pyplot library, which with as PLT. This is a very, very common practice to name this PLT. Even in standard data scientists, some things have become very, very common. For example, pandas become PD, NumPy becomes NP, PyPlot becomes PLT. All right. Okay, so he has already added that. I don't have to do it. So it is, I like this practice of always creating a PLT.figure, creating a chart with PLT.figure. Even if you don't provide it, PyPlot will create a chart and create the necessary drawing. And even if you don't write PLT.show, it will show it. But it's a good practice to keep these two together. Okay. So what we are doing is we are calling the scatter method, and X and Y are the arrays that we want to plot. Marker we are using star, and the size of the figure is going to be 20 by 10. Okay, let's execute this one. And there it is. We can see the chart. Is it visible to everyone?
Yes, sir.
Yes, sir.
Okay, great. So before we proceed, there are a few things I would like to demonstrate about PLT charting. Just a few things, not more. So let's say if I want to see the vertical and horizontal grids also, how can I do that?
PLT.grid.
PLT.grid. Right. Typically, of course, if I don't follow any put anything, it will take true, but I'm going to provide it true. So if you provide false, that means if there always already have grids being shown on the chart, they will be turned off. This is how it will look like. Okay. What happens if I want to provide the x title to x and y axes?
PLT.x label y label.
Yes. So on x label, let's say x feature, and y label y. All right, there you see, but they are very small in size. Can we increase the size of this text?
Yes, give the argument size.
Very good, very good. So those of you who do not know this, these things will come very, very handy. See this one. Now it's much more clear to understand what's going on. If if a chart is properly labeled, it is more readable. All right. Okay, let's move on to the next part. Okay, so at this point, I think you already know what a model is. The next task is what is a model and how would you write it? And of course, we know both answers to both of them. So I'm going to skip this one. Okay. Geometric interpretation of the model. Okay, so before we move on to the next parts, what do you think a model will look like if it has only one feature?
Straight line.
A straight line in what kind of space?
2 dimensions.
2 dimensions. Very good. And what happens to the model, or how does it look like if there are 2 features?
Hyperplane.
Hyperplane in how many dimensions?
M+1.
M plus, and what is M here?
3.
Right. So M plus 1 becomes 3. So in 3-dimensional space, you are going to get a plane. We typically call it hyperplane because in higher dimensions, it is not easy to visualize. These planes are not possible. Therefore, we call them hyperplanes. All right.
So why does the second one have line in it?
It's just an option, right? It's wrong.
Okay, right.
Right. So even for this question, only line is the correct answer. Plane, polynomial curve, and the option 4, all 3 are wrong. For question number 2, only hyperplane is right. Line, circle, and 4th option is wrong.
Circle will not be correct in any case, is it?
Circle will not be correct in any case. Yes, I don't think so. Can you imagine any case in which circle?
Yes, it could be, or 2D also. Is it not possible?
So
Then
circle
it's probably not a very well conditioned problem, because for 1x you're getting 2y's. So circle is not a function. If we remember from maths 1, it's a relation, it's not a function. And if we end up with that kind of a regression problem, then you're essentially solving two different regression problems. Because for the same x, you're getting 2y outputs.
Right.
Also, but circle can be used as a
polynomial regression.
No, but as a decision rule.
Yeah, for classification, it can be used, but even say for example regression, if you use a polynomial regression, then your surface will be it can be a circle, right?
It could be but a semicircle.
No, but even in polynomial regression for 1x, you'll never be capable of getting two different y outputs.
Right, you will be using a semicircle for it.
Okay. So for one upper half, you can use one model, lower half, you can use another model.
Yeah.
Right. And one more thing, there are techniques like I'm going to give in something that is going to come up in week 8, where you can get circular boundaries, but for that you have to transport your data into higher dimensions. Something for you to look up. We are not going to worry about it. Support vector machines, yes.
Yes. Yeah.
Kernel function, right?
Yes.
We increase it to TUVs, if I'm not wrong.
Right. So that will be covered in SVM. So Shreya was it, right? Who asked the question?
No, sir, it was me, Shruti.
Okay. So please watch out for that in week 8. That will come up.
Okay. So would you also point us to any other resources, perhaps some MIT courses or something?
For what exactly?
The entire course, something that we can look through alongside or something. Anything that you think will be useful?
Okay, I can certainly point you to some study material, which are books mainly. So which part do you want for this regression itself? You want some help with?
Yeah, I don't know. For some reason, I'm not able to catch up as fast as everybody else.
Oh, so you can tell us, right, in the forums as well as in this session is for you. Tell me if anything so far that you have problem with.
I actually had posted a question about not understanding the 3 types of gradient descent that that you guys had shared within week 1.
Okay. So the mini batch gradient descent is stochastic. Okay, I'll answer that post. I'll make sure that I read it and answer it. All right.
Yes, sir. Thanks, sir.
Sure. And gradient descent is coming up in this session. All right. So next task is write a function that takes in weights W0 and W1 as parameters, and that function plots the model. Okay, so this is
we have to use the same data.
Yes, we have to use the same data, and not necessarily. No, this one is different, right? This one is not asking to. This one is not talking about the data points. It is saying that you have M and C. So W0 is C, and this is M. If you have these two, draw the model. Right? This is the question.
So that means W0, W1, we can initialize to anything, or?
So you have to write a function
so
that takes W0 and W1. Right.
Okay.
So even the data also will be a parameter, right? Obviously.
So for this one, I don't think data is a parameter in this one, because it is not talking about data at all. All it is saying is draw a line if you have W0 and W1 with you.
Oh, but then how would we draw the line without dx?
How do
we draw the line without dx, without the data?
Without the data, good point. So see, if I give you a line like y is equal to mx plus c, I give you a line like y is equal to x plus 2. All right. So let me write this one.
Okay. You want to? It's a function that draws a straight line. That's about it.
Exactly. That's all. So for that, if you want to draw it, typically what we do is we take some sample values of x. Okay, I assume that x starts from -5 and ends at +5. And what are the values of y, and just plot them, something like that. Okay, I have received answers from Jaidev. And I have received answers from Ganesh also. Okay, I have received answer from Tanveer also. Good. So 350 points. Okay, all of your answers are actually correct. So far the answers that I've received. So let me copy one of them. Let me copy Ganesh's answer. There it is. The function name is plot model. Good. It has two parameters, W0 and W1. Okay, for x, you have taken random, you have generated random numbers between 1 and 61, and there are hundreds of them. All right. Then you have created the y, and then you have created this chart. Okay. Instead of scatter plot, this time I would like to just draw the line plot. Okay, the reason for that is we already know that there is no randoms involved in it. Okay, so let's execute this and plot a model. Let's draw 4,4. Let's see what happens. Okay, there we are going to see a very straight line. Yes, there is no randomness, and the inclination, I mean the angle of this line with the x-axis is going to be 45 degrees. Yes. No, not 45 degrees. It is going to be more than 45 degrees. Sorry.
No, the aspect ratio is not.
Yes, you're right.
Equivalent.
All right. So I think this is done. Any questions for this one?
Because the randint, I think, is a little suboptimal here, because if you want to pick random integers between 1 and 61, there can't be 100 of them. Right? There'll be repeated values in x.
Yes, definitely. There will be repeated values.
If we just convert it into a random number, random float or something, then that will be. We'll get
okay, so yeah, I think your point will be more clearly visible by this, right?
There are some even there, because they'll be overlapping.
Yeah, and some spots are empty. There are spaces between the points.
Yeah. So one question.
Yes.
Typically we take W0 to be the constant, right? And W1 to be the slope. Of course, it doesn't really matter. We can just define it, however, but the convention has been to take W0 as the dummy thing.
I totally agree with you. Yes, this is the convention. Yes, we should do it like this.
But I think this is a convention that's peculiar to this course. Mostly we stack the column at the end, right?
Okay.
What have you seen typically? Is it at the beginning or at the end? Like ignoring this particular course?
Okay, so in this course, we are following this consistently that the dummy variable is going to be added at the beginning of feature matrices.
Okay, okay.
All right. So this works. We could do this also. This time we will not. Sorry.
Yeah, that random.
No, there's no random. It's just
np.linspace.
Still is showing error. That is interesting.
Spelling, space.
Oops. Yes. All right. Now we are seeing a very uniform data points. All right. Okay. Let's go to the next task. So now, Srinivasan sir, when you were saying that where's the data, now I think we are going to come to that point. Now we are supposed to compute the loss function. So by loss function, we are trying to determine how far away our model that we have at hand, how far it is from the data points. Okay. So take 2 minutes and try to write a function for this.
Sir, do we need to find the square error with respect to just the the normal whatever we are doing right now, like y is equal to mx plus c, or the general one?
Now y is equal to mx plus c is not going to give you the yeah, good point. So right now you are writing a function, but you don't have a specific value of predictions as of now. Okay. So yeah, the sum of squared error or mean squared error, both are fine. All right, I have started to receive answers. Jadev has written his answer to compute the error. All right, couple more answers from Rajiv and Deval. Okay, so Rajiv has written in the proper format, which is demonstrated in the book itself. Okay, yes, that's nice. All right, all right. I think we can proceed now. So I'm going to take Rajiv's answer for this one. Very nice and clean. It has feature vector X. It has feature vector, sorry, the label Y, the weight parameter W, okay, and then it returns the loss. So before we move on, this single line, compresses a lot of details. So I'm going to, put that in separate lines. So this also becomes C. All right. So can anybody tell me what is this doing?
So it's a matrix multiplication, no?
Okay. Of what?
Of weights and features.
Okay.
Features
And what? Yeah. What is it going to give us?
It will give us the predict thing. Yeah, predict. We had the predict function. I know
Absolutely
what
right.
it is.
Yeah, absolutely right. So this is going to be our prediction. So if you multiply feature vector with the weight vector, we are going to get the predictions for all those samples. Right? Hello?
Yes, sir.
I think it's the predicted labels, na?
Pardon me?
This is the predicted labels, na? X at the rate W, this thing.
Yes, exactly.
Yeah.
So maybe I should write it like y hat or this. So whatever the predicted values were, we are subtracting the actual labels, the ground truth labels, and E is going to be a scalar value or a vector.
Scalar value.
It is going to be a scalar value. Okay.
Sir, I have a doubt.
No, it will be a vector.
Yes. Please go ahead with the doubt.
Sir, when we're defining the function, so even y and w will be vectors, right? So shouldn't they be capital as well?
Y and W should be vectors. They should be capital. Okay. So this is up to us. I mean, I understand your point. In the lectures, everywhere we have denoted vectors with bold, small letters, and matrices with capital letters and bold. However, in programming part, we cannot put syntax like that. So we are keeping them small. That's fine. I mean, if you want to keep them big, that's also okay. But the convention we are following right now is the vectors are denoted by small variables.
Okay, yeah, I just wanted to confirm that both of those are vectors as well.
Yes. Y is a vector, X could be a matrix, and W is also a vector.
W will be a matrix, right?
W should be a matrix of what size?
Depending on the number of weights you choose to have. W0
let's say
and
we have two
W1.
features. Then how many quantities will be there in W?
So the number of records in X
3
cross 2.
Okay, so you are saying that if we have two features in X, then let's say Okay, let me write this one.
Oh yeah. No, only two, right? Only two, because weights will remain same for all the records.
Yes.
Got it. Okay.
Something like this, right?
Yes, sir.
Okay. And to my question, E is going to be vector or scalar?
It's a vector. I'm sorry, I said loss will be a scalar. My bad.
Okay, it's all right. So E is going
So
to
again, to
be
be consistent, there are two features. There will be 3 weights, right?
for two features. There will be 3 weights. Something like this. So is this clear?
So what example you have given, we have to add the dummy feature too, right?
Yeah. So for that, we already have the dummy feature, right? Which is W0.
No, the dummy feature.
Pardon me?
The dummy feature.
Dummy. Right. Dummy feature is going to be 1. And for that, we have already taken care of the weight, which is W0.
No, don't we have to add those dummy features to X?
Yes, of course we'll have to add. Otherwise, this will not work. This will not going to work. Yes. So good point. Let's do this. Let's create a random model. Let's have W is equal to, we already know 3, 4 is the solution, or 4, 3. So let's create 5, 4. So our intercept value is 5 and W1 is 4. So we have a model. So this is all we need for a model. And we already have the data, but we have to, concatenate it with the dummy feature so that we can multiply our data with the weight vector. Can anybody tell me how can I do?
Column stack.
Yes.
Column stack. np.column stack.
Yes, write the code for it.
Sir, what are we referring to as dummy feature, and why do we have it?
Right. So dummy feature is something which is not part of the original data set, but we add that constant feature just to include this bias term. Okay. So see, this is our data, right? We have X on the X-axis, feature on the X-axis, there is only single feature, and the label on the Y-axis. So you can see that it is not data, even if it is a line, it is possible that it does not go through the origin, right?
Right.
So for that, we have to, if we create the model, we have to take care of that bias term or the intercept term.
Okay.
Right. And therefore, our model comes out to be MX plus C, right?
Yeah.
Okay. So for making sure that we take care of the intercept, we add this, but we have to train our model on the data also. So what we do is we add this dummy feature and say that, okay, its weight is W0. The dummy feature is always 1, because we multiply it with W0, we get always W0.
Okay, right. Oh, so you'll have a row in the X matrix that's just a column in the X matrix that's just 1.
Exactly. That's right.
Okay. Got it. Thank you, sir.
So I've received some answers from Rajiv, Ganesh, Tanveer. Okay, so I'm going to copy Tanveer's answer. Let's see. Yes. So he has written code like this. I'm going to remove the capital M. So we are using column stack, and we are going to create numpy.ones and going to pass x.shape0. All right, and then x. Okay, so this is doing a lot of things for us. So let me break it down. All right. So one thing is this. And okay, so I'm going to do a very poor breakup of this code just to specify what different things are involved in here. Okay, so first thing that we are doing is we are going to create a column vector or a single vector with which has only ones, but its shape of that or the number of elements in that dummy feature will be exactly the number of samples in the data we have, right? And the number of samples we are going to get is from this one. So I can write it like number of samples. So this is my this x dot shape, and inside 0, if I pass that, I'm going to get the number of samples. After that, see this function is going to end over here. So what is this? If I pass this value, the number of samples into numpy.once, what am I going to get?
All ones.
All ones, and the size of that vector is going to be
100 by 1.
100 by just 100, not 100 by 1.
Yeah.
Okay. Yeah. In when we write a vector on notebook or a page, we always say that it is n by 1, but in NumPy it has just 100
100
entries.
comma.
Yeah, it has only one dimension. Okay, so this is going to give me vector of ones of size 100 comma nothing. So it has only one dimension. All right. And the next thing is our original data. So you can see this comma over here. So we are passing two things. One is the dummy feature with all ones in it, and the second thing that we are passing is our original data. So what we are saying by calling this function is column stack. Stack these two items that I'm passing inside this function column wise. So they should be put side by side. Okay, so I'm going to execute this. Let's see. Okay, okay, it executes, and let's see the shape of X now. Okay, there we see that there are 100 rows and 2 columns as expected. All right, and we can see some 5 numbers from our modified data set. 5 rows and all columns. Right, now you'll observe that the first column is all ones and the second column has the data. Okay, any questions so far?
No.
All right, let's begin. So this is only one step before calling the loss function. So we have our weight vector, we have our modified data in which we have added the dummy feature. We also have our labels. Now all we have to do is we have to call this function to compute the loss. And let's do that exactly. We're going to pass X, we're going to pass Y, and we're going to pass W. So before I pass W, it's a good practice to convert this into a NumPy array. And then if I execute it, this is going to give me the loss. Okay, so this is the sum of squared error. Okay, so if I multiply 2 divide by 100 and then take the root of that, I'm going to get the root mean square value. So let me copy this into some variable which is t. How can I transform t into root mean square value?
You wanted to convert to RMSE, right?
Yes, t into RMSE.
Yeah, np dot square root t. np.sqrt,
Okay.
2 by n, 2 divided by x dot shape 0.
Okay.
2 divided by x dot shape 0, and then entire thing multiplied by the t. But 2 divided, yeah, you surround that with.
Will this work?
Yeah, and 2 divided by x dot shape 0, you surround by a parenthesis, bracket.
Ah, that's fine. It will
Okay,
work.
okay, yeah, it will work. It will work.
Yeah. Okay, let's execute it. Oops, there is some error. T is not defined. Why? Oh, yes, there it is. So the reason I asked you to compute this RMSE is because we get a specific number. So on an average, the prediction of our model that we just created, for every point, it is 38 units away. So we can interpret it like this. And of course, it is not a very good model. Now let's again guess another model and try to see if it comes close to our data. So let's take this. Instead of 5,4, let's go a bit closer to that. Let's say 4.5 and 3.5. That is our weight vector. And then we compute the loss. Now you can see the values has changed since the model has changed. Can anybody tell me what is the has it increased or decreased?
Decreased.
It has decreased, right? And this is how we are going to measure how good or bad our model is. Okay, so we can certainly say that this model is this model is better than the previous one, which was 5,4.
Sir, in the root mean square formula computation, why did we add the 2? I did not understand.
So we added, we multiplied by 2 because earlier when we computed sum of squared error, we multiplied by half.
Okay, and so, why so?
It's a practice. If you go into if you look closely at one of the videos, it is only for the sake of convenience, because later when we differentiate the loss function with respect to w, right? Okay. So this half gets cancelled out by the square that 2 that we get after differentiating the square term.
Okay, right. After differentiating, got it.
Yes, yes. All right. Any questions so far?
Actually, I'm getting an error when computing the loss function.
Can you share your code with me?
I'm using the same code as yours.
So you have to give me some hint. What is the error?
The error is numpy.float64. Object cannot be integrated as an integer. I don't know why.
Object cannot be integrated as integer. So I think there is some mismatch error. This is what it looks like.
Okay, let me see that.
All right. Or at the end, if we have time, you can show me your screen and we can figure it out. Okay.
Thank you, sir.
All right. So, all right, let's move forward. Now, this is the point where we have figured out what is a model, how we compute that that model is close to our data set or not. That means whether it is good or bad. Now what we want to figure out is how can we start with any random model and still come up with a very good model, which is very, very good representative of our data set. So, one thing that we were just trying was kind of trial and error. Okay, so we took a model, we computed the loss, we took another model, computed the loss, and figure out that the second loss is smaller, therefore it should be better. Of course, we could do that, but it is time consuming and not going to guarantee us any good results. Okay, so what we do is we follow a couple of algorithms by which we can compute the optimized solution or a model which is very, very close to our data set. Okay, so let's, so there are these three, so these questions that we should talk about. All right, now that we know what is trial and error method, what do you think we should be a better algorithm, trial and error or using some definite algorithm?
Normal equation.
Definitely, some definite algorithm. Good. And what about
algorithm? So
yes, yes, sir. Was there any question? Okay, okay, let's move forward. So why do you think an algorithm is important rather than trial and error? Which should be the answer to this question?
Yeah, I think it both the ways.
Right, right. So if we go with the trial and error, we have no upper bound on how many times we have to try. Okay, so that could be very, very expensive. And this and it doesn't guarantee to converge to the optimal solution also. So for both of these reasons, it is good idea to use a proper algorithm. Now, in this session, we are going to cover two of them. One is the normal equation, and the second method is the gradient descent. Okay, let's work with the normal equation. So write a function which returns pseudo-inverse of a matrix A. We can you can assume that A is actually numpy array. Right. So I've received answer from Jaydev. Use the linear algebra library class from NumPy. That's fine. Also from Tanveer, very similar answer. Right. Right. Ganesh also. Rajiv, thank you. So all of your answers are actually correct. So this one, it involves only writing one line of code from NumPy. So let's do this. Okay, so if A is a matrix and we want to calculate its pseudo inverse, this is how we are going to do it. Let's execute this. A is equal to let's say 6. Okay, let's see. All right, before I proceed, just a side question. What is this reshape function?
Helps you assign a different shape to the array.
Right. And why am I passing -1 over here?
To copy.
Not the number. We don't want to put the number of rows, so we want to keep it undefined, and then number of columns is going to be 2.
Exactly. That is the right answer.
So we discussed this in the morning, sir. So that's why. So
I see. Okay. Great. So glad to know it has already been covered. So whenever we write -1, we want the library to figure out what should be the number of rows. If you put or what should be the number of items in that particular dimension. If we are putting 2 in the column, that way we are saying that this is the number of columns I want, and figure out what is the number of rows that should be there. So it will compute 6 by 2, which is going to be 3. Okay, this is all. Okay, so we have computed the answer. All right. So anyone of you, if anybody was wondering why this way to calculate it, actually you can calculate it the exact way in which sir has mentioned in the lectures, which is x transpose x multiplied by x transpose y. That is also possible, but both of them are going to give the same answer. Okay. So now we know how to calculate pseudo inverse. And so this is one method. Now what we are going to do is write a function that uses the concept of normal equation to find the weights of the model. And for this one, we are going to use the data that we created, which is x and y, using y is equal to mx plus 3, m was 3, sorry, mx plus c, m was 3, and c was 4. All right, I've received an answer from Ganesh. Okay, Rajiv has also answered. Yes. Hi, hi everyone. I'm really sorry for the interruption. Actually, there was power outage, and it took me a few minutes to restore the internet connection. Hi, I'm really sorry for that interruption. Actually, there was power outage. So where were we? We were talking about computing the weight factors with the help of normal equation, and I had received several answers from all of you. So now I'm going to type just one of them. Is this the right one?
Yes, sir.
Okay, let's execute it. Oh, it is taking so much time because I had disconnected from the runtime, so it might even produce errors.
Yeah, I think you need to run all.
Oh, it did not produce any error. Let's see what the W is coming up. All right. So as somebody had mentioned earlier that the RW, the weights should be very close to 3 and 4, and you can see they are actually 3 and close to 3 and 4. Not exactly 3 and 4 because we have added some noise to it. Okay. So now let's try to visualize this model that we have computed here with our original data. Why? So this will be our blue data and x comma x at the rate w with red points. You can also change its transparency. Let's keep it 0.2. Okay, and for 0.8. Okay, there's something wrong with it. X multiplied by W, this should be our production. Okay, so the error is not over there. Maybe I'm using something incorrectly. Okay, this is where it is wrong.
So I think you can run all the previous cells once, because not sure if it is taking the correct X.
Okay, good. So somewhere here we generated the data points with the help of linspace function, which is this one. After that, we actually created our augmented data set, which was here. Then coming to this one, this is also there. No, we are still having the same problem. I think there is some shape mismatch issue. Let's try to print that. That is also not an issue. What's
No, it is giving some different issue like SQRT, some SQRT. Yeah, now it is working.
Now it is working. Okay, maybe I provided a wrong answer for wrong parameter for the color. Okay, all right. So you can see that the blue points slightly difficult to visualize this without the transparency setting. But now you can see that the blue points, which are slightly behind the orange predictions, they are very close. They are very, very close. And we can also compute the loss of this model, which is around 50 units. Not 50 units, I would say. This is sum of squared loss. So quite low as compared to the losses that we got, like 35,000 or 3,500 and then 1,800, things like that. So now we have only 50. Any questions so far?
No, sir.
All right, great. So let's go to the next one, which is the gradient descent method of computing the optimized weight vector. So before we proceed, can you tell me what happens if the data set is very, very large? Let's say we have 100 gigabytes of data, something like that. So it has millions to billions of records and maybe hundreds to thousands of features. Then how we are going to compute this one? Is it still possible if we do this, or it will not be possible with such a large data?
It will take long time actually.
Okay.
Even it might go out of memory.
It might go out of memory. Okay. All right. So actually, think about this. So X, when we are computing the pseudo inverse of matrix feature matrix X, the entire matrix is actually copied into the main memory, which is the RAM, and then this operation of computing the pseudo inverse is performed. But if the data set is very, very large, for example 100 gigabytes or something, and we have examples of even larger data sets, if you want to compute pseudo inverse of feature matrix, it is not going to be possible because of the memory constraints. Okay. So for large data sets, it's not possible to go with the normal equation method. And therefore, it is very, very needed that we get an algorithm which is iterative, okay, which computes or takes our solution, takes our weight vector closer to the actual minimum of loss function step by step. All right. Now your next task is compute the let's say if you have some weight vector W, compute the next set of weight vector parameters after computing or executing one iteration of gradient descent. So for this task, you can assume a function like X, Y, there will be one more parameter which is called alpha. W. Okay, I've not received an answer for this one. Is it taking a longer time than expected?
So, okay, you have W. So, like you need to calculate the grad as well, right?
So for this one, you will have to compute the gradient with respect to W. Okay.
Correct.
Add or subtract that gradient with the current weight vector and get the new weights.
So this is the line actually your return statement. Oh, sorry, alpha. Multiply the alpha.
Right, Rajiv. For the answer that you have posted, that assumes that the alpha is 1. Right?
Yeah, I forgot that alpha. I send the next one.
Okay. So, all right, you are typing answers this quickly.
No, I'm writing in a Google Colab and then copy pasting this that here.
Okay. Okay, I've received answer from Rajiv and Ganesh, both of them, and both of your answers are actually correct. Let's go ahead with Rajiv's answer for now. So this is, if you go through the lecture slides, you can directly get this formula. You can easily compute this gradient value. So you can see this. This is actually gradient dj by dw, which is the gradient function. And now what happens is we want to go in the opposite direction of that gradient. Therefore, this negative is over there, and also we want to we want to take care of the alpha, the step size. Okay, so this is definitely going to compute the gradient. Now let's apply this one and observe some interesting results. Okay, so let's say my W, I shouldn't say W1, or okay, for now let me just write it W, with which we start numpy dot 5, 4. So let's say we could have initialized our initial weight vector with any other values, but this is one that we choose. All right. W iteration 1. So W after first iteration, pass it X, we pass it Y, we pass it our original vector, and for alpha we pass let's say 0.01. Okay, there is some error. Let's see what the error is. It's not defined. Okay. 2 and 200. What is something is wrong over here?
No, I think this W you need to change the shape.
I don't. 2 and 2 by 100.
So I think it's the transpose and the other one.
Okay. This is Y. This is transpose. I think this should work, right?
Yeah, it should work. W54.
Operands could, the error is definitely belonging to the shape mismatch error. Is definitely that one. So let's see this one to debug this, and this is very well possible. This happens a lot of time. See the shape of this. So the shape of this is 100. Okay, and the shape of this should be 2 by 100. XYW. This is 2 by 100. Then 2 by 100 multiplied by 100 by, it should be
matrix multiplication, right? I mean, we should put an at symbol there.
Thank you so much.
Yes. That was.
Yes, it is working now. You know, this kind of things happen a lot of times when you are working on some complex code. Even this is not that difficult code to understand, but yeah, things like this slip in. So now we have computed W underscore iteration 1. Let's compute the loss for both of these models. W and W underscore. Whoa, what is happening?
Yeah, your learning rate, like, you need to reduce.
Yeah, possibly. Yes, we need to reduce learning rate to something even smaller. So right now, what is happening is, if learning rate is too large, we are overshooting our minima, and that's why it is growing. Still, it is growing. So I have to choose a very small learning data. Right now, for this learning rate, you can observe that the error earlier it was 75,000. Now it is 73,000. So slight decrement in one iteration. Okay, so the idea behind this gradient descent is we keep doing this small upgradation until there are no improvements, and by this we are going to get a weight vector which is very close to the optimal solution, or actually very optimal. Yes. All right. Any questions?
No, sir.
All right. So before we close the session, let's do a couple of things. So one thing is, let's visualize these two models that we have got, the W and W iteration 1. Okay.
We have that plot function as well, right? Like, you can give just the W.
Right, but the
On top
range,
of,
I'm not very sure. We have to make sure the range of all our original data points, and this is also exactly same, right?
yeah, it will be, because I think, like, that lint space was taken 100 something, that sort of.
Okay, for now let's do this. This should also work. Right, there it is. Okay, maybe I can remove the original data points for just now. Oh, so first one is here, second one is over here. So both of them are actually, this should not be the case, right? How come they're very, very close?
No, actually now there are two guys, like one is orange, another is blue. Blue is behind orange. So instead
Right,
of like placing this dot, like you can just give a line plot, right? Use PLT dot plot.
Right. No, what I'm saying, Rajiv, is I was expecting that there should be a larger difference between blue and the orange lines.
Oh, okay.
Yes. So maybe let's start with this one, 15, 14. Let's see.
Swarnim, change in the loss function doesn't always is like, I mean, better print W, na?
So yeah, definitely we can print the W, but we want to see visually that after one iteration, our model is actually
what I'm
closer
saying is
to.
print W and then we'll see if there are actual differences. Now, how much difference that will be.
In the weight vectors, right?
Yeah.
Okay. So see, first, I think we should make the difference even slightly bigger. Let's see what happens. Now I think it is making sense. Yeah, there it is. So see, I should put the label also. Or there it is. So this is our original, the W1. So I think I should plot this one also then. All right, now it is much more clearer. So see, the blue points are the original data points that we want. That is our original data that we want our model to be very close to it. W is the orange line with which we started. And after one iteration, we got the green line, and you can definitely see that it is slightly inching closer towards the data that we have. Okay, so in this way, we can visually inspect that actually our model is going closer and closer to the optimized solution. Okay, so any questions? This is something that you can also try and see on your own. This is going to give you a lot of confidence that actually this method works by creating this, from scratch.
So I had a question on one of the lectures. Like, can I raise that now?
Sure.
So one of the testing codes uses I mean all the testing codes actually use an object called unit test. I was not quite clear on the implementation of that. The test class that is implemented. Can you please explain that?
Yes. So unit tests are used for making sure that we do not introduce any bugs into the code. So for example, we want to test what should be. So what we do is we write.
If you could just take that same one which is there in the lecture and explain, it'll be helpful.
Actually, I do not remember that one right now. Can I request you to write a discourse post? I'll make sure that I'll handle it.
Okay, sure. So yeah, then maybe you can just explain what unit test does. I'll put it in the discourse for a detailed question.
Sure. Right. So let's say we create our model. So unit tests are there for sanity checks also. So what we want to do is, let's say we create a model and we want to make sure that that model does predict good values for some of the data points. All right.
Okay.
So let's do this one. Okay. We compute not next vector, but
it was used for gradient. Okay.
So let's say we have this solution. We want to make sure that no matter what we make changes in our code, our certain conditions are always satisfied by our model. Okay, so I'm going to give you some conceptual information about that, not the exact unit test class that is there in Python. Okay. So this is our W. Okay, and let's predict some of the values, which is, let's make predictions on first just one value. Okay. This is incorrect.
Sorry, your
okay,
W
so
is
this one prediction is over there, right?
Yeah.
Okay. So what we want to do is we want to make sure that this is supposed to be very close to the actual y value. So let's print that also.
Your W is PLT.scatter.
Yes. Hello.
Yeah.
Okay. So so this is one condition that we can impose on our model. For example, we can always write assert that this thing.
Yeah. Got it.
Dot absolute less than 0, or not less than 0, definitely not less than 0, but let's say 2. Okay, some manageable error. So when we are training our code, so this is one example of what we can put a condition on our model, that after training the model should be something like this, so that its prediction on first sample is less than the error on the first prediction is less than 2. So what is this going to help us? So let's say the error is not less than 2. So this kind of condition will be checked by a unit test, and it will raise a concern or raise a warning that something is wrong with your model.
Okay. But the same thing, like why do I need a unit test? Like I can use assert without that also, right? Like why do I need the unit test in a class? Like
okay, so again, this is an example of what kind of condition you want to check. In unit test, this gives you even more I should say fine-grained control over your model. You can put all sorts of things. You can put I mean, of course, that is unit testing is also a way to check conditions on your model or your program. You can write assert also, but unit test gives you a proper structured way of doing this.
Okay, got it.
And also it gives you some kind of a code coverage. Actually, it is a covering on your code, because say for example you have you have written a 10 lines of code, and tomorrow you are changing that code, right?
Yeah.
So you do not know what are the areas it will go and break. So if you have the unit test written, you can run once and you can see if all passes, then only you can push that code to commit that code to some code repository.
Okay, got it. Thank you. Okay. So one other question was learning curves we can plot the way we've done for the other things also, right? Like in using matplotlib itself. It was not, the code is not discussed in the lecture, so I just thought we can I can do that in the same way using the number of iterations and the values of W, right? With the same.
Absolutely.
Okay.
So that's a good point. So why don't you try and take 2 to 3 minutes and write a code to visualize the learning curve for this particular setting.
Okay, I actually missed a few things in the middle, so I don't know if I, but I'll try it for sure and post it on Discourse.
Okay, sure.
Yeah. Okay. Thank you.
So for everybody else also, I want to ask this question. Go ahead and now you know how to compute the weight vector for the next iteration. Go ahead and create this learning curve. Of course, I'm extending the time a little bit. I hope that is okay. Or anybody has something else to give time to? So is everyone okay? And can we do this last exercise before leaving?
Yes, sir.
Okay. Okay, you guys need still more time, or should I proceed?
Sir, actually, not all the codes, like whatever you have written, is in like our collab.
I see.
So that is the reason it is showing like now we need to start from like a beginning kind of.
I see. Okay, so I understand. So let me, since for the sake of for the minute of time, I can finish this one. Okay, so let's say the number of iterations are 100. Okay, and we are going to we will be computing the loss, right?
Loss, yeah. Yeah, that is
I should write losses, something like this. Okay, so it's an empty array. All right, and what we have is I want to initialize W with this one. Let's keep it like this. Okay, what I want to do is I want to compute W from with the help of this method. Okay, and then compute the loss.
But sir, actually, like you need to calculate the initialize the W and then calculate the loss, because here
Yes,
what
yes,
you
yes. You're right. So I executed this cell, but yeah, it's
okay,
a good
okay.
idea. We should keep this in this cell itself.
Yeah, so your loss dot append it should go up actually.
Ah, I see, I see. So
It should be within the
No, inside that for loop, like before you
gradient
would
descent, right?
yes, like before you wrote that W equal to compute next, right? Before that line, like write that losses dot append. There you calculate
uh,
the loss.
okay, but see,
Because
there will be mismatch for one entry. I want to compute the loss for first entry also. If I do that, there will be one iteration. The last iteration will be lost, right?
no. Like inside that for loop, right? First you compute the loss with the W that
Okay,
you have already initialized, right?
something like this you are saying.
Right, because W has already been initialized.
So that means the last weight vector that I'm calculating, for that I'm not computing the loss, right?
For last weight vector, whatever you are returning.
Yeah, that's correct. I mean,
Okay.
I think it should be at the end, the losses dot append. Yeah.
Yes, something like this. Okay, so after doing this, all we have to do is we have to print this, to plot this losses array. Let's execute it. It executed fine. Now plt dot plot. It should be, I think,
X equal to np dot arrange 100.
losses.
Okay, yes.
Okay. Oh,
No,
I made a
the
mistake. Range of this thing.
range, yeah. np dot range length of losses.
There it is. And now it is coming out to be very, very smooth and very, very nice. So around, I think, 10 or 15th iteration, it was very, very close to the optimal solution. And after that, we were just doing very, very small corrections that are not visible to eye. Okay, so before closing, any questions that you would like to ask?
Sir, I think someone in the someone asked that SGD mini batch and GD difference, right?
Mm-hmm.
Someone has asked, like, if she is still there, like she can ask that question probably.
Okay, so for mini batch and stochastic gradient descent, you can still experiment with exactly in this manner. You will have to change the update rule though, right? For where did it go? Compute weight vector. Instead of taking the entire
X,
you'll have to take some part of it. For stochastic, you take only one sample. Iterate through entire data set, taking one sample at a time. Compute the loss. Compute the gradient, and computing the new weight vector, computing loss, and drawing a chart like this. That will be interesting to see. You can try this on your own. And for mini batch, you have to set the size of the batch. It could be 2, 4, 16, 100, whatever you think should be there, and you can start working with that. So for mini batch, so that's an exercise you should do. I will highly encourage you to do on your own.
Yes. So basically, it is another for loop outside the gradient descent. Where you
Another
are
for
breaking the X, breaking the X.
This one here?
No, like yeah, here also we can do that actually.
Yes, you can. You have to modify this piece of code.
Correct. Like only like breaking the X, because if I put this as a function, right? There, like inside that function, whatever X I will be giving as an input, that X I'll give X by N, X by K.
Exactly. So I think you will have to add couple of lines over here, and your code will change into stochastic or mini batch.
Correct.
Yes. You have to take care of one thing though. Every time you take the some samples from X, they are new. I mean, you're not repeating, going over the same samples again before looking at the other samples. That is the only thing you will have to take care of.
Sir, can you come again? Like,
right. For example, you are taking some samples of X in this line, right? For stochastic or mini batch. You will have to make sure that the samples are not, you go through the entire data set before repeating the data set.
Right. Yeah.
Yes, you have to take care of that.
Correct. We'll do that actually. We'll write that.
Okay.
And sir, another thing, like in the lecture videos, here has also plotted that how the W is like how the W is moving and using a black curve, right, in that contour plot.
Okay, so you are talking about that contour plot or 3D curve, is it?
Correct. So can we get a kind of a code snippet or some idea like how we can plot that kind of things, like a contour plot? Okay, we can plot, and then on top of that, like I'll have to place that W and kind of a line we need to plot, right?
Right.
How the W is changing.
Okay, so I'm going to give you a hint on that. You can try on that, and if you still have some questions, please post in Discourse. I'll definitely answer those. So this is something I wanted you to try at the end of this Solve with Instructor session. I thought if we had more time, we will address that also. So first, you will have to think about that. What is a loss function? So loss function will look like a bowl in 3D space, right? For this particular data set.
Correct.
And the any instance of weight vector is going to be a point on that loss function, loss surface. Yes. So what will happen is after every iteration, here we are only keeping track of the loss. You can also keep track of your W's.
Correct. That's what that bookkeeping is done in that gradient descent code.
Yes. So here, right after this, you can write W. So in this manner, you are keeping track of all the weight vectors also along different iterations, along all the iterations. And all you will have to do is you will have to plot these W vectors, individual W vectors, as black points on that loss surface, and you will get the answer.
Correct. So in the plot, PLT.plot, my X coordinate will be W0 and W1 will be the Y coordinate.
Exactly. And Z coordinate will be your loss.
Right. Okay, I'll try that.
All right. So you will have to, you will get three, in 3D space, you need 3 coordinates. So W0, W1 you will get from here, and Z you will get from this losses.
Correct. But if I'm plotting in the contour plot, then I don't need that Z, right?
Exactly. In that case, you don't need that Z. Yes.
Because in one plot, I will say contour, and on top of that, I will start plotting these W's.
Sure. Yes. That's exactly right. Okay. Any further questions?
No, I'm fine.
No, sir.
All right. Thank you, everybody, and thank you for the patience you have shown, both in the middle and at the end, by allowing me to extend it by so many minutes. Thank you so much. Have a good day.
Yeah, it's a great session. Thank you so much.
Thank you, sir.
Okay. Bye, everyone.
Thank you, sir.